All right. We're going to be working the 6.1 homework and going to be using the integration by parts formula, which is going to require that I fill out a table. That's the way I do it. And so we'll always have to be able to pick within our integral a choice for u and a choice for the dv, and then we'll differentiate down to get du, which will appear here. We'll integrate up to get v, that'll appear here, and then we'll try and redo the integral. So let me start with number one. Or sorry, what is this? Yeah, number one. And get integral x squared natural log x dx. Okay, so I need to first realize this is not any of the other techniques, so I don't see a basic substitution. But I do see that these two functions separated by multiplication, that if I take my natural log and I take the derivative of it, I get 1 over x. And then if I integrate this, I get 1/3 x cubed. And when I put those two together, so again, I'm trying to think ahead here. The derivative of this being 1 over x, the integral of this being 1/3 x cubed, that if I multiply these two together, that's just going to be a power of x, and that's a good thing. So I know my new integral is actually going to contain something I can handle. So I believe that'll be a good choice. So I'll start my table off. My u, I'm going to use natural log x. My dv is going to be the x squared and the dx. Everything else that was left up there. What the heck's going on over there? All right, derivative of u is, we said, derivative natural log of x is 1 over x dx. And then the antiderivative here of x squared is our v, which is 1/3 x cubed. And now I will rewrite using my formula. So this will be equal to ultraviolet, which are these two multiplied together, 1/3 x cubed natural log x minus a new integral, and then v du, which is going to be, hello, v, which is 1/3 x cubed, times du, which is 1 over x dx. And so now this becomes 1/3 x cubed natural log x minus, I'm going to bring the 1/3 out, integral, and then I have an x cubed divided by an x, so this is x squared dx. Y'all can talk. It's not, you don't have to be quiet.
I was watching the video that you posted.
Oh, shh, please. Keep it down. Keep it down, please. So the antiderivative of x squared is 1/3 x cubed. And then now I can do plus c. So negative 1/3 stays. Antiderivative of this is this, plus our constant, and this should be it. What were you saying? You were watching my video, what?
Well, nothing. Very interesting video. Very helpful.
Oh, good. Well, I wasn't sure if anyone was going to show up today, so I started making videos for the next section. So, but I'm open to help you out if you have questions. I'm just going to keep working through these if that's all right with you.
Yeah.
Okay. All right.
I have a question.
You ready? Yeah. Yep. Yep. number 2. te to the negative 3t. te to the negative 3t dt. Y'all okay? Okay. All right. So again, we're going to have to do some sort of substitution. So which one of these gets better if I take the derivative? So derivative of t would just be 1. So that's actually going to get really nice in the new integral. The antiderivative of this, I should be able to handle. So let me try that as my choice here. U is t. dv is the entire thing that's left, e to the negative 3t dt. And then du is just 1 dt. And then the antiderivative going up here, you have to be a little careful because this is not just going to be e to the negative 3t. We're going to have a negative 1/3 e to the negative 3t. And that you can see if you do that on the side here. Just a separate problem here. Let u be equal to negative 3t. du would be negative 3 dt. You don't have a negative 3, so you have to scale it by negative 1/3 du dt. So what happens is you rewrite this integral e to the u times the 1/3, negative 1/3 du. And then that will turn into this. So, all right, so that's that. And now, this is equal to ultraviolet, so negative 1/3. That's this. I'm going to multiply the t. I'm going to put the t here. E to the negative 3t. Then minus, here's my new integral voodoo, which is going to be across here like this. So I'll have negative 1/3 e to the negative 3t dt. And I can pull the negative 1/3 out and make it a plus. Integral e, oh, forgot the third, 1/3 e to the negative 3t dt. We just did this integral, and so we know this what this one turns out to be, but we have a plus 1/3 in front. So negative 1/3 t e to the negative 3t plus 1/3 times antiderivative of this, negative 1/3 e to the negative 3t plus some constant. And then put these two together right there. We should be done. Minus 1/9 e to the negative 3t plus c. That's it. Anybody have a question?
The answer for 27 doesn't, it doesn't feel like it's going to derive correctly.
You mean like if you check it?
Yeah.
Let me see. Wait, the one you just did?
Yes.
That one?
Yes. The answer that I got, I don't feel like it's going to derive correctly.
You got secant squared?
I got
1/3
yes.
secant cubed
Yes.
of x
Plus C.
plus c. So the derivative of this is chain rule. 3 comes out, it's gone. Secant squared x times, now derivative of secant, which is
Oh, okay, got it.
secant tangent x, and then derivative constant 0, and that's secant cubed.
And you can put this in.
Yeah,
Okay.
yeah. All right, x cosine 5x dx. All right, if we take derivative of x, it's going to get better. It's going to become a 1, and then we can find the antiderivative of this. So I think that's a good choice. U is x. dv is everything else that appears. Derivative down here is going to be du is dx. And integrating this, antiderivative of this is 1/5 sine 5x. And so this becomes ultraviolet. Those two multiply together. Minus integral voodoo, which is across like this. And so 1/5 sine 5x dx. I'll pull the 1/5 out. So this is equal to 1/5 x sine 5x minus 1/5 integral sine 5x dx. And then the last step is take the antiderivative of this. So 1/5 x sine 5x minus 1/5. And then antiderivative here, we have another 1/5. We have negative, actually, because the antiderivative of sine is cosine. 5x plus c. And then put it all together. So 1/5 x sine 5x plus 1/25 cosine 5x plus c. That's it. Questions? No, questions? Questions for you? No? Okay. This integration by parts is pretty much going to be kind of like the substitution. You just have to make that first step. If you make the first step correct, it all works out. But it's getting that first step that can be a trouble spot with these. Okay. For integral y e to the 0.2 y dy. Let's see what this text message was. All right, so for this one, this is very much like, oh crap, did I skip 2? Oh man, I did 5 instead of 3, oops. Okay. The one that I said was number 2 was actually number 5. So let me do this one. This is very much like number 5. It's rough. It feels like Monday squared right now. All right, so if I take the derivative of this, I get 1, or just dy, and then I should be able to integrate this pretty easily. So my choice of u here will be y. My dv will be everything else. The derivative of y is just dy, or 1 dy, and then the antiderivative here will give us v, and I have a constant in front of the y, so with the basic substitution we would get 1 over 0.2 e to the 0.2 y, and then 1 over 0.2 is actually 5, so this is just 5 e to, yeah, this is number 2. I messed up. Wait, no, this is 4, this is number 4.
Oh, no.
Okay, so ultraviolet minus voodoo. So this times this, so I'll put the 5 in front, then the y, and then e to the 0.0, or 0.2 y, minus integral voodoo is this times this, so I'll go ahead and get the 5 out now, e to the 0.2 y dy. And we just integrated this just a second ago. We had to do that when we went from here to here, so we know it's going to pop this out. So I'm going to have another 5 that comes out with that. So our answer will be 5y e to the 0.2y minus the 5 times the 5, so 25 e to the 0.2y plus c. That's it. See if I can get back on track. So I'm going to do number 2 now because I accidentally did number 5. So number 2 is theta cosine theta du. D theta, sorry. D theta. So you ask yourself which one gets easier, which one gets nicer. So theta gets nicer, derivative of theta is 1, or just d theta, and then you can take the antiderivative of cosine. So u is theta, dv is cosine theta d theta, and du is d theta then, and v is sine theta. So this becomes ultraviolet theta times sine theta minus integral voodoo is diagonal, so sine theta d theta, and that antiderivative of sine is negative cosine. So you wind up getting a plus there because your negative comes out and hits the negative. So you're done. Question? No?
I have question 26, but
Okay.
I think I might just need the unit circle. It's cosine pi over x over x squared times dx. So I was going to look for the unit circle. I don't know if I needed to use the unit circle for this one.
You need to look for something in its derivative. You need to figure out what you're going to use for substitution there. So do you see something in its derivative? All you're going to get off the unit circle is just values of cosine, which you don't need because you're looking for a function and its derivative sitting there in front of you, right?
So for you, maybe I use cosine?
The whole cosine, well, you have to use the whole thing. If you're going to use cosine, you got to take everything that's inside of it also.
So cosine pi over x?
Okay, so if you use that for u, what is its derivative? And then if you do it, its derivative needs to be there in the problem, right?
Yes.
So what's going to happen?
It becomes negative sine.
Okay, do you have negative sign?
I do not.
You do not. So probably not. That was you chose too much. Okay, you got too much because when you tried to take the derivative, it was right. So don't try and grab so much.
What if I use the pi over x?
Okay? That's the correct substitution. Now see if you can figure out why it's the correct substitution. You have to take derivative of pi over x.
Since the pi is a constant, it stays the same?
Stays out front, yeah, pi. You can look at that as being pi times 1 over x.
And then that becomes 1 over x squared.
Negative 1 over x.
Negative.
Yeah.
And we do have an x squared, so...
Just peel it all apart. Like rewrite it, peel the sign out front, and then put that x squared that's on the bottom right as a 1 over x squared on the outside. Okay, so for this one, I'm going to try and pick a u and then a dv. And these are in parentheses, so I can choose this whole thing to be my u. The derivative of this is just dx, which is nice. This one would be my dv, so I have to be able to integrate that, but I should be able to integrate that without any issues. So again, x minus 1 dv sine pi x dx. And so the derivative of this is just 1 or just dx, and then v we integrate negative 1 over pi cosine pi x. So this would require doing a little u substitution on the side, but I also showed you in class how to actually do this quickly. So it goes to that, and we should go straight to the formula now. So ultraviolet is the first one times this one. Make sure you leave that x minus 1 in parentheses. Times this. You know what? I'm going to redo that. I'm going to put the constant out front. negative 1 over pi is my constant, x minus 1, and then the cosine pi x. Okay, minus integral, I'm going to run out of room, so minus integral of this, negative 1 over pi cosine pi x dx. And the negative and negative become plus, so this equals negative 1 over pi x minus 1 cosine pi x. Negative negative is plus, 1 over pi, and now I need the antiderivative cosine pi x dx, which again I can do that. Antiderivative cosine is sine, but I have to take care of the pi x, so I have to scale by another pi. So negative 1 over pi x minus 1 cosine pi x plus, no more integral, okay, because I'm going to do it right here. I have a 1 over pi, but then I got another 1 over pi here, so 1 over pi times 1 over pi is 1 over pi squared, and then I have sine pi x plus c. So this is it right here. Number 7. Now we start getting a little interesting. Integral x squared plus 2x cosine x. All right. So now we have a little bit of an issue, because if we choose this to be our u, the derivative of it is 2x plus 2. So my new integral is going to have a 2x plus 2. Antiderivative of that I can handle, but that's not much better than this one was. Also, if I let this be u and I take derivative, I can get negative sine x, but then the antiderivative of this becomes something with x cubed in it, which I don't want in my new integral. So let's just see what happens. This is going to be one where I have to do integration by parts twice. So u is x squared plus 2x dv cosine x dx. So what I'm thinking is that, again, when I take the derivative here, I'm going to get 2x plus 2. The new integral is going to have a sign in it, and it's going to have the 2x plus 2. I'm going to repeat the process. I'm going to do integration by parts again in that new integral, and then I'll be able to reduce this one down one more time. So let's just see it happen. So du is going to be 2x plus 2 dx. V is going to be sine x. So this should be ultraviolet, x squared plus 2x sine x minus integral of voodoo. So it's this times this. And I do have a pretty ugly looking expression there. 2x plus 2 and then sine x dx. So this new integral is not that much better than this one, but notice that the power has come down. So I went from a quadratic expression to a linear expression. And if I do integration by parts one more time, I'm going to take the linear expression down to a number. So I will repeat integration by parts. Do you have a question? Or give me that look. Yeah? Okay, I'm almost done with this one. V is equal to negative cosine x. Derivative here is 2 dx. Okay, so now this is important that you get everything written down. What we're going to say is that this was our original ultraviolet minus voodoo, but this new voodoo had another integration by parts. So everything here is now going to require this integration by parts. So I'll write down the original answer, which was that. So this was my original ultraviolet minus, now here comes my new integration by parts, which is going to be this table, ultraviolet minus integral voodoo. So this times this, that negative's here, so be careful. Negative 2x plus 2 cosine x minus integral again, voodoo, the diagonal. And notice this voodoo I can do. So the negative and the 2 and cosine x dx. So negative 2 cosine x dx. And now on that one, I can do minus minus, that's plus, and then take the antiderivative. So I'm almost done here. So this was the first example, or the first homework problem that I've done where I had to do integration by parts twice. So x squared plus 2x sine x minus, now this minus and that minus become plus, plus 2x plus 2 cosine x. And then we said this, I'm not going to do the integral yet, but I have minus and minus, which come plus 2 out here, but then minus. So minus 2 integral, so I distribute that negative through here. And then I have cosine x dx. And the antiderivative of cosine x is sine x. So my last line and my final answer will be x squared plus 2x sine x plus 2x plus 2 cosine x minus 2 sine x plus c. And that is the antiderivative. Okay, what's up?
I understand how to do it. I used to
All right, this one's very similar to number 7 because you have quadratic.
Wear glasses.
And so if you do integration by parts one time, it's going to come down to a first degree. And if you do integration by parts again, it's going to come down again, and it's going to be a constant. And we can do antiderivatives of this all day long because it's just going to keep cycling back and forth between cosine and sine. So I'm already anticipating integration by parts twice. U is t squared. dv is sine beta t dt. Now du will be 2t dt, and v will be antiderivative of sine, which is negative 1 over beta cosine beta t. Always having to take care of that number in front of t. Remember, beta here is just a constant that we don't know. So we've got ultraviolet, so this times this, negative 1 over beta t squared cosine beta t minus integral voodoo, which is this way like this. And so we have a negative 2 over beta cosine beta t dt. I forgot my t. There we go. T. There it is. So that t right there. And I'll pull the negative 2 beta out. So negative 1 over beta t squared cosine beta t plus 2 over beta integral t cosine beta t dt. And I cannot do this integral. So I have to do integration by parts again. So I'll do that, I guess, in red. So just this part right here is a new integration by parts, a new table. This time, keep my u is going to be the linear or the linear expression in t, and then the dv will be the cosine because I can integrate that. And then du will be dt, and then v will be 1 over beta sine beta t. So derivative down, integral up, and now I'm going to rewrite everything in red using ultraviolet minus integral voodoo again. So here, right here, this is equal to negative 1 over beta t squared cosine beta t plus 2 over beta, and then here comes my new ultraviolet minus voodoo. So ultraviolet is this times this, so 1 over beta t sine beta t. Okay, and then minus integral of voodoo. So minus integral of voodoo is 1 over beta, and then sine beta t dt. And that's all in brackets. All right, so everything in this bracket is what I got from this, which was a new integration by parts, and I had a 2 over beta out in front. So what I'll need to do is actually now find the antiderivative of this, which should be pretty clean because there's no more t here. And then I'll distribute the beta through, 2 over beta through. Be done. So negative 1 over beta t squared cosine beta t plus 2 over beta. I guess I'll distribute this right here. No, I'll wait. Okay, 1 over beta t sine beta t. All right, I have a negative 1 over beta, but when I take the antiderivative of this, I get negative sine, or negative cosine, but then I also have that beta in here, so it'll be negative 1 over beta cosine beta t times negative 1 over beta cosine beta t. And then that's it. I'll have a plus constant. I'll put that at the very end. All right. Almost done. These problems are getting longer and longer and longer. So negative 1 over beta t squared cosine beta t distributing through plus 2 over beta squared t sine beta t distributing through. Negative negative is positive, plus so plus 2 over beta 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 cubed cosine beta t plus c. That's it. That's number 8. Hey, what's up?
What?
That's
Why are you asking?
I've always loved you.
what am I on?
Did you really just say you
31
always loved me?
Yeah.
What time is it? 10:40.
I do that.
Natural. Oh, this one's nice. Okay. Integral natural log of 2x plus 1 dx. All right, so I'm looking at this. Do I have a basic substitution? No. Do I have anything else? Now, you don't even think that integration by parts is going to work here either, because you really only have one factor. I mean, this is it. You don't really have two functions. But you can always look at this as being like a 1 dx. So let's try something here. I'm going to set up my integration by parts. I'm going to let u be that natural log thing. And that forces me to use the 1 dx as my dv. This may not seem like it's going to work, but it is. Du, the derivative of this, is 1 over it times the derivative of what's inside. So you should get 2 over 2x plus 1 dx. And then the antiderivative of this, well, the antiderivative of 1 with respect to x is just x. And so now we have ultraviolet, this times this, x natural log 2x plus 1 minus integral voodoo, which is this times this. So that becomes 2x over 2x plus 1 dx. And then how would we integrate that? So you can't split that up into two fractions, but I believe we can do a basic substitution here. Let's do this. Let's let u be equal to the whole bottom. And then the derivative of that is just the derivative of the top. The derivative of that is just 2 dx. Now we don't have a 2 dx, we have a 2x dx. So let me rewrite this integral and write it this way. X over 2x plus 1 times 2 dx. So I have a 2 dx right there. I have the 2x plus 1 right here. But I need to replace the x. So what I'll have to do is I'll have to take this equation. We've done this before in the previous homework assignment. And we would solve for x. So u minus 1 equals 2x. 1 half u minus 1 equals x. So solving that equation for x. Replace that x with this. So we have integral 1 half u minus 1 over, so that's just this, over this, which is u, and then this, which is just, where is it, du. I'm going to work backwards this way. Take the 1 half out, integral, this is u minus 1 over u, split that into two different fractions. U over u is 1, minus 1 over u, which is 1 over u, du. And now the antiderivative of each of these, I'm working backwards. Antiderivative of 1 is 1/2 u, because the variable is u. The antiderivative of 1 over u is natural log, so I have another 1/2 because I distribute that. Natural log absolute value of u. Now, what was u in this problem? It was 2x plus 1. So if I take this expression and I replace the u's with this, that's equivalent to this integral. So that'll be my next line. So my answer here was x natural log 2x plus 1 minus the antiderivative of this, which are these two pieces. So I'll put them in brackets. 1/2 u, 1/2 u, 2x plus 1, minus 1/2 natural log of u, which is natural log of 2x plus 1. All of that, plus some constant, and then I can distribute the negative through, which will change that to negative, and I'll change this to positive, and no more bracket. So that should be the final result. Yeah. That's it. I'll see you guys. Huh? Do you have a question about this?
For your unit cells right there, where did you get u as?
Okay, so I took this right here, and I subtracted 1 on both sides, which gave me this. Well, because in... Well, yeah, that's the derivative right here. See, here's the problem. This integral, right, is what I'm trying to find this integral. Forget everything else. And there's really nothing easy you can do, but if you, this is a basic substitution. So this is what your homework was on last time. I'm going to let u be the bottom, right? Then du is 2 dx. But see, I have an x in here. I have 2 dx, but I have an x there also. So I need, if I rewrite this integral, bring the 2 dx to the back, I've got that. 2 dx is du. Over here, the 2x plus 1, I've got that. That's u. But x itself, I need to replace. So I take this equation, I solve it for x. So I move that over, divide by 2. That allows me to rewrite that top. Make sense?
Yeah, that makes
Okay.
sense.
Nice.
Okay. So
Looks like we'll see.
I'll see y'all, right?
Maybe. Yes.
In a couple hours.
House.
Is that supposed to be a sign?
No, it's,
See you later.
All right, we'll see. Okay, I should be alone here now and maybe work through this a little quicker here. Ooh, yuck. Okay, we have number 10. Integral p natural log p dp. Wait, p to the 5th natural log p dp. All right, so this one is a little bit counterintuitive, I guess, because you might initially say, hey, look, I can pick p to the 5th because when I take its derivative, it becomes p to the 4th, 5p to the 4th, and I know I can do integration by parts again and get it down to p to the 3rd, and then p squared and p, and then eventually go away. So you know that repeating the integration by parts over and over, you should be able to reduce that power from 5 down to p, 5 down to a constant. Here's the issue, though. Taking this one, you'd have to integrate. And how do you integrate natural log p? That's a little more challenging. Differentiating natural log p is easy, though, because that's just 1 over p. And integrating this is relatively easy. So it looks like if we choose our u to be that natural log p and let dv be everything else, which is the p to the 5th dp, then du will be 1 over p dp, and the antiderivative here is 1/6 p to the 6th. And now look at our voodoo. Our voodoo, we have a p to the 6th, and then we have 1 over p. That's going to cancel one of the p's. We'll get p to the 5th, and that we can integrate. So this should be pretty clean. So ultraviolet, this times this, 1/6 p to the 6th natural log p. So I'm putting these in like a standard order. We like to put numbers in front, then powers of our variable next, and then any sort of weird function, trig function, log function, exponential function would come kind of towards the end. and then minus integral voodoo, which is this times this. So 1/6 p to the 6th times 1 over p dp. One of these p's cancel, it becomes a fifth power. The 1/6 is going to come out. So I have 1/6 p to the 6th natural log p minus 1/6 integral p to the 5th dp. The antiderivative of p to the 5th is 1/6 p to the 6th. So I'm going to get another 1/6 next to that one, which will give me 1/36. So minus 1/36 p to the 6 plus a constant. All right, number 11. Arctan of 4t. I'm going to write it this way. Arctan 4t dt. So this is like that problem we had, I think it was number 9, where it was just the natural log, and it didn't seem to be anything else we could work with. But in this one, this one appears to be the same thing. We only have one thing here. So you've got to choose something to be u. Never choose your differential to be u, because if you take derivative of the differential, you get almost like a second derivative, and we don't want to mess with that. So let's just try u being that whole arctangent thing. dv will be forced to be the dt. And now the derivative of arctan of something is 1 over 1 plus that something squared, 16t squared, times the derivative of what was in here, which is just 4. So I'm going to make that a 4 on top, dt. Now here we integrate up, and the antiderivative of dt is just t, because the derivative of t is dt. And so this should become ultraviolet, which is going to be t arctan 4t minus integral voodoo. So voodoo is this times this. That t comes and hits this, becomes a 4t on top. So integral 4t on top over 1 plus 16t squared dt. Now if you look at that, notice that that is a basic substitution. If I make a basic substitution here, okay, so this is a new integral. I'm kind of done with the integration by parts. A new integral, I'm going to let u be the bottom. The derivative of that is what 2 comes out, so 32t dt. I have a 4t dt, but not a 32. So if I divide both sides by 8, 32 divided by 8 is 4. 4t dt. So I tried to make this turn into a 4, so I had to divide by 8 on both sides. So I can replace the 4t dt with 1/8 du. I can replace the whole bottom with u. And so this new integral right here becomes integral 4d dt is 1/8 du. And then that's my 1/8 du, this part. So I'll still have like a 1 over this, which is u, 1 over u. And the antiderivative of 1 over u is natural log. So natural log u. And then that's equal to 1/8 natural log of u, but u is 1 plus 16t squared. So I know that this integral is going to become this. Just don't confuse the u here with the u there, because this was a different substitution. This right here was to get us the integration by parts formula, and then that was a new integral, so I could do any new substitution I wanted to. So my final answer is going to be this part here. So t arctangent, or times arctangent of 4t, and then I have minus this, minus 1/8 natural log 1 plus 16t squared plus some constant. And I'm done. Okay, I think that's a good point to stop this video. I'm going to come back and do a couple more.